standard deviation is still close enough to the x, the airplane won't crash into a tree or something like that, then I have a 99% chance that my system is reliable. If I don't know that it's Gaussian, I can't estimate how reliable the system is. But because it's Gaussian, I can say exactly it's 99, it's 95, it's 68. Okay? So the symbol for standard deviation, the symbol that is usually used is this Greek letter sigma. This is a lowercase sigma. When you read the literature, if you read journal articles, if you read commercial articles in the industrial world, you'll hear people talk about 6 sigma. Who's heard about 6 sigma? You're going to hear about that a lot when you go to work. What does 6 sigma mean? It means 6 standard deviations. What's the probability of being outside of 6 sigma? It's 1 minus the probability of being inside of 6 sigma. 6 sigma is something like 0.9999, I don't know what, 5, something like that. So your chances of being outside of 6 sigma are maybe 1 out of 10,000. So companies talk about having 6 sigma reliability. I'm building Honda motorcycles. The motorcycles come off the end of the factory. There's always a chance, every single motorcycle, the parts that go into it were manufactured one at a time, right? Maybe this cylinder is a little bit bigger than that cylinder, right? There's always some chance that you get a bunch of errors that add up just wrong, and that motorcycle doesn't work. Okay? You'd like to know what's the real probability. You want to make sure that probability is something greater than outside of 6 sigma. 6 sigma means something like 1 in 10,000. You can't have 1 sigma. 1 sigma is only 68% reliable. If 32% of the motorcycles coming out at the end of the factory are not reliable, people are not going to buy it. Right? When you buy a motorcycle, you expect to have a better chance than 68% that it works. In fact, you expect 100% that it's going to work. But 100% is impossible. But 6 sigma will get you really, really close to 100%. So this is kind of an international standard. It's based on 6 sigma, and that comes from the Central Limit Code. Good stuff. Okay. Let's quickly look at this. Long window. Yeah, so I think I just said all of this stuff. Yeah, here's an example of extrapolation, right? We're going to find the total amount of lumber in a wooded area. You can't measure, you could measure all the trees, but that's probably not practical. So you measure a few trees, calculate the size of that, and then assume that that's a good representation of the whole forest. So multiply by the area of the whole forest to get the total number of trees. Do you really know that that's the total number of trees? Of course not. But it's hopefully, if the ones you measure are close to the average, then when you extrapolate, it should be close to the right number. Yeah, so let's pause before we go on to the next one. Look at these words over there on the left. Are there any of these definitions that don't make sense? Magnitude is the size of the variable. Magnitude does not take into account the sign, plus or minus. Plus 100 and minus 100 have the same magnitude. The magnitude is 100. Observation, that's a single measure. So if my process is rolling a die, I roll it one time, it comes out 4, my observation is 4. It's one value, one measurement out of something that goes on and on. The parent population, that's all the possible outcomes. The parent population for rolling the dice is 1, 2, 3, 4, 5, 6. The observation is what happened on that roll. A sample is a group of measurements. You could have a sample that's only one observation. Error is the difference between the thing that you're trying to measure, if you're making a measurement, and what you actually measure. give you an example. Another example. I could bring in a meter stick, and I can take everybody out of the room, and one at a time, you come in here and I give you the meter stick, and you tell me how long the room is. I'll bet you that out of 40 people, I probably get 40 different answers. Hopefully they're not off by very much, but they probably are 40 different answers. Okay? There is one length of the room. There is some right answer. If I get 40 different answers, at least 39 of them are wrong. How much are they wrong by? The error. That's what the error means. So you hope that the error is small, but who knows? You don't always know. Accuracy is how close to the right value. Precision, the closeness of a group to each other. So that's like standard deviation. So let's say I bring the meter stick in and you're supposed to measure. If everybody gives me a measurement that's within, say, 2 centimeters, and the length you give me is 40 meters, plus or minus 2 centimeters, that's good precision. That's a very small error of the total length. But let's say the length is 40 meters, and if you measure 10, you measure 90, you measure 35, that's terrible precision. Right? It's useless because the range is so big, it's totally unreliable. But if you give me 39.8, you give me 40.2, you give me 39.7, 39.9, 40.1, okay, that's good precision. Okay, precision and accuracy are not the same thing. Because, for instance, if this is the example of the ruler, let's say I tell you that the thing is 1 meter, but in fact it's only 95 centimeters. So every meter you measure is going to add 5 centimeters to the error. So your error is very precise. Everybody has an error that's really close to each other, but you're all off because the underlying measurement itself wasn't good. So that's precision means the errors are close together. Accuracy means it's actually the right answer. You can have a very precise measurement that's not close to the right answer. That's error. Okay? So here's an example of a histogram. This is what I was doing with the dice. So this is an example where you could have an output of 4, 2 students had a 4, 4 students had 5, 7 students had 6, 8 students had 7, and so on. That's a histogram. You could make that in Excel now. You could easily make that in Excel. This is an example of the difference between median and mean. We talked about this before. So the median in this case is 7, but the mean, if you calculate it, is 6.91. That's the actual average. But the grades are all integers. The grade is 4, 5, 6, 7, 8, 9, and 10. So even though the average is 6.91, nobody got a 6.91. That's not a possible score. But half the people got above 7, half got below 7. Now, this is an example where I said earlier that usually to get an exact median, you have to have an odd number of samples. Actually, that's not quite true because in this case, there's 8 samples that are 7. So which one is the one in the middle? It doesn't matter. Right? The total number of samples is 2 plus 4, that's 6, plus 7 is 13, 8 is 21, 6 is 27, 3 is 30, and 2 is 32. So this has 32 total scores. The median is either 16 or 17, right? Half above and half below. Where are 16 and 17? This is 2 plus 4 is 6, plus 7 is 13. 16 and 17 are both 7. So it's correct to say that the median is 7. Even though there's 32 samples, so there actually isn't one in the middle. There's 16 and 16, but there's nothing exactly in the middle. But the one on the edge of the high 16 and the one on the edge of the low 16 are both 7. So that's the median. Okay? So this is what I talked about before with the dispersion. It's the average of the difference squared between the median and the value, and then take the square root. So that's standard deviation. This standard deviation comes out to be 1.55. So let's pause for a minute. So we calculated the grade is 6.91 is the average. Standard deviation is 1.5. So if this distribution is Gaussian, what does that tell us? If I subtract 1.5 from 6.9, I get 5.4. If I add it, I get 8.4. So according to Gaussian, 68% of the scores are somewhere between 5.4 and 8.4. That's what this calculation says. Two standard deviations would be add 3, or minus 3. So from 6.91 minus 3 would be 3.91, plus 3 would be 9.91. And this says 95% of the scores are in that range. That's what the Gaussian distribution tells us. See, here's a plus 1 sigma, minus 1 sigma. So this is just showing you how to make the calculation. Alex, let's go back to that last slide for just a second. Okay. So this works. Remember, the central limit theorem says if you add enough randomness together, this is a relatively small sample, so it may not be perfect, but let's see how close it is. So plus and minus 1 sigma is supposed to be 68% of the scores. We have a total of 32 scores. In this range, we have 7 plus 8 is 15. Plus 6 is 21, plus 4 is 25. 25 out of 32 scores. 25 out of 32 are in the range of plus and minus 1 sigma. What is the 25 out of 32? I don't know off the top of my head, but it's not far off of 68%. It's a pretty good prediction. Even though it's not really a big number of data points, it actually predicted it pretty well. Does everybody see how that works? Okay, it's cool. Okay, that's cool. Okay, so pause again for a minute. This formula, you know how to do this, but I'll just point out in case it's confusing to you. So there are 32 scores, but there's actually only this many different outcomes. It's either 4 or 5 or 6 or 7. So to calculate the average, he's multiplying each score by the number of people that got that score. So there were 2 4s, there were 4 5s, there were 7 6s, and so on. But you still divide by 32, and that's how you get the mean. Now that you have the mean, you have to sum over a total of 32 scores. So 1 over 32 times, and there are 2 of them that were 4s. You put in 4 for the x and 6.91 for the average, square it. So it's even when it's below the average, so this is a negative number, when you square it, it's always positive. So remember Gauss liked those least squares? When you calculate standard deviation, you're squaring all of these errors. So the ones that are on the high side of the mean, they come out positive inside here, they get squared and they stay positive. The ones on the negative side of the mean are negative, but they get squared and they're also positive. So when you calculate the standard deviation, you can only calculate a positive number. So there's a hint for you. If you ever write a program and you calculate a negative standard deviation, you made a mistake. It's impossible to have a negative standard deviation. The pieces that you use to calculate it, they're all squared values. They can only be positive, or at the minimum, they can be 0. But they can't possibly be negative. Okay. Yeah, so we talked about this too. The more values you have, the smoother the curve gets. So here's the Gaussian distribution. I told you I couldn't remember the mathematical expression. There it is. So here's the math expression I couldn't remember. 68% of the area, like I told you. 2 sigma is 95%. Okay, 3 sigma is 99.7%. This information is about how to adjust the estimates based on the size of the sample. I think it's good information, but it's a level more detailed than what you need at this time. Yeah, see? formulas allow us to estimate how large the sample should be in order to think that we got the right answer. I don't know if this happens in polling in your country, but when there's an election in our country, before the election, they always ask some people how they plan to vote. And then from that, they predict the outcome of the election. So they say, this guy's going to get 42%, that guy's going to get 38%, she's going to get 15%. But they've only asked a few people, they haven't asked everybody. So how reliable is that prediction? It turns out it's not very reliable. But you can use these calculations to predict how unreliable it is. So instead of saying he's going to get 42%, I say he's going to get 42% plus or minus 4%. So actually he might get 38, he might get 46, somewhere in that range. How do I know plus or minus 4%? This shows you how to do it. This tells you how reliable your estimate is. So the 42% is probably a perfect calculation of the data that I have. So I go out and I ask 50 people, how are you going to vote? 21 people say, I'm going to vote for this guy. So if 21 out of 50 say for him, then I can say 42%. That's a real calculation. However, I only asked 50 people. If the election has 5 million, what are the chances that the 50 people that I asked are actually a good representative of the 5 million? There's some chance I didn't ask the right 50 people. So this helps you to predict how reliable your prediction is. Okay. And this is an example of that last slide. Okay, we're over now. I love this confidence interval stuff. This will be a good place that we can stop. So we talked about one standard deviation having a confidence interval of 68%. That's the chance that if we sample the value, it's on one side or the other. Now I want to say something about multi-dimension. Let's go to the end of this. Okay, so you're done. Let me say one more thing for a second about these confidence intervals. If we have one random variable, right, it looks like this Gaussian curve, and we can predict 68% inside of one standard deviation. Suppose there are two random things happening at the same time. So I can make a two-dimensional plot. And there would be another curve that would be Gaussian going in the other direction. So the two of them together look something like a hill. But the size of the hill, the width of the hill, depends on the standard deviation. And the height depends on the mean. And it wouldn't have to be the same in the two directions. So rather than looking like a round hill, it looks more like an oval-sized hill. Right? More like a rugby ball, not like a soccer ball. So now suppose I have three variables. Instead of looking like a hill, it looks like a sphere in space. If the three variables have the exact same mean and standard deviation, it's perfectly round. But if they have different ones, then the lengths along each axis are different. So now it's like this distorted three-dimensional shape. Okay, that's called a confidence hyperellipsoid. Confidence hyperellipsoid. So let's say I'm trying to predict the position of my airplane. The airplane is flying in and I'm trying to measure with the radar. The measurement from the radar starts here, it goes out, it bounces off the plane, and it comes back. My measurement in this direction should be pretty accurate because that's where the radar is bouncing. How about my measurement, say, above the ground? It's not so accurate because how do I have to estimate that? I have to estimate that when I have my transmitter or my receiver, I know the exact angle above the horizon. And also I calculate this distance correctly, and then I can use this distance times the sine of that angle. And that's how I predict how high above the ground the airplane is. But there's more probability of having error in that direction. And what about this way? There's a lot of chance I have error in this direction, right? Because I have to know the exact angle that the radar is turning this way to know that. So I'm measuring a three-dimensional position of the airplane. but the accuracy in the 3 dimensions is not nearly the same. So what's my confidence that I know what the airplane is? It looks like a shape like this in each of the 3 directions, but those shapes are different sizes in the 3 directions. So I end up with some kind of big football kind of shaped thing. And the airplane is inside of that football somewhere, but it's a lot longer in one direction than it is in another direction. Okay? So how do I design my runway? I'd like the plane to hit here. Right? I need to know the errors in those 3 dimensions in order to decide, do I make the runway wider? Do I need to do that? What's my confidence side to side? How long should I make the runway? Where should I put the touchdown point? Right? This looks like wasted runway. If I'm going to hit that point, I don't really need this runway. Except I'm not sure I'm going to hit that point. I only know the plane is inside of this big shape in the sky. My confidence high for ellipsoid, I don't know perfectly where it is. So I use the estimate of this confidence ellipsoid, that shape. I put that over the end of the runway. I pick something like 6 sigma. And so I make my runway 6 sigma wide based on this prediction. I make this 6 sigma based on this direction. Right? The third direction is altitude. The altitude will cause the plane to go longer or shorter. So altitude also gets added into this direction. That's how I decide how to build the runway. Everybody understand that? At least a little bit. Any idea what I'm saying? Okay, so I'll start over again real quickly. So I'm measuring the airplane with the radar. Oh, if I have the radar calibrated correctly, the median of the error, the median of the measurements that I'm making, the mean, I hope this has a 0 error. But it doesn't have a 0 standard deviation because it's not perfect. So the real airplane is somewhere inside of here. It's not at 0 all the time because there's a little bit of error. Now I'm designing the runway. I don't want to crash my airplane. I want my airplane to survive. I calculate the solution for the airplane to land based on hitting a point out here somewhere. But I don't build an airport. I don't build a runway that's just that point. I build a runway that's quite a bit wider and quite a bit longer. But how long and how wide should I build it? How long and how wide I should build it depends on what is this value. Because inside of this range, 68% probability. 68% is not good enough for my airplane. Airplanes are too expensive to crash 1 out of 3 airplanes. It costs a fortune. Okay? So let's build it 2 standard deviations. Well, 2 standard deviations is only 95%. Airplanes are too expensive to crash 1 out of 20 airplanes. Let's build in 3 standard deviations. 99.7. Okay, now we're getting closer. That's still 3 out of 1,000 airplanes crashing. And a really busy airport in the world, like say Chicago is a really busy airport, or Paris or something like that, they have maybe 5,000 flights a day. This probability is 3 in 1,000. So that would be 15 crashes a day. I don't think so. Okay? Better not stop at 3 sigma. Right? But this is the point. The point is, the reason why these statistics are so important is it enables you to make that calculation. So I calculate what's a 6 sigma. 6 sigma is 1 out of a million or whatever it is. I don't know the number, but this is exactly how they go. And then they come over here and they say, okay, my landing system can predict this point. That's where it's supposed to land. 6 sigma gets me over to that edge. 6 sigma gets me to that edge. That's good enough. That's how wide I'm going to build our runway. Okay? Where's the touchdown point? How far should I come in from this end? At least 6 sigma. However, I could go 6 sigma too long and land out here. Then the plane's going to roll a long way, so I better add some space down here, another 6 sigma down there. Real world, that's how you have to do it. You cannot rely on getting the exact answer every time. So you need to have some idea of what is the error that you're likely to calculate, and take that into account for your design. That's exactly what this is. Beautiful. It's beautiful stuff. Thank you. What time do you want to meet tomorrow? Morning or afternoon? Afternoon tomorrow. Morning tomorrow. Okay, I better count. Afternoon again? 1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3.